Okay, so let us continue with our study of the photoelectric effect. Basically, what we're trying to understand is the process of an external electromagnetic radiation basically causing the electron in the hydrogen atom to rip out of the hydrogen atom completely. Okay, so what we're left with is an ionized hydrogen. So we are trying to understand this process by considering the external electromagnetic radiation to be a classical field, while we are assuming that the hydrogen atom is a quantum mechanical system. Okay, and we understood yesterday that the relevant Hamiltonian to understand this is basically H tilde, the perturbation is H tilde that depends only on position times e to the minus I omega t, where H tilde of R is given right above this line, which is E over 2mc e to the I k dot R times an A dot P kind of interaction. Okay, so let us try to understand this a little more, this Hamiltonian. So first of all, notice that the K and R, e to the I k dot R and A0 part all belong to the external electromagnetic radiation, right? So these are all to be treated as classical quantities. So the R here should not be considered as an operator in the Hamiltonian. The only operator here is the P right here, okay? So that is the first thing. Now, we're going to try and understand a little bit more about this K to see if we can simplify this Hamiltonian. Okay, so this is a simplification that is perhaps strictly not necessary, but it is still a very useful simplification because it will teach us something about the physics of the system. Okay, so what is this K? So what is this K? The K is basically the momentum of the electromagnetic radiation. So I'll use interchangeably photon electromagnetic radiation, because even though I'm not quantizing the electromagnetic field, I'll still use the word photon because it's easier. Okay? So K is the momentum of the photon. So what is the photon doing? The photon is basically causing the electron to get out of the hydrogen atom completely. Now, suppose if the photon were only causing a transition between one level of the hydrogen atom to another level of the hydrogen atom, then what should be the energy of the photon? The energy of the photon, to cause a transition is basically h bar omega, and this should be of order of magnitude 1 Rydberg. Okay, so this is basically E square over A0. A0 is the Bohr radius, is called 1 Rydberg. Okay, which means the momentum of such a photon should be momentum of the photon to cause this kind of a transition would be energy over C, because for a photon, remember that E is P times C. So this will be in a momentum is h bar times k. This will be equal to E over C, which is h bar omega over C. And this is approximately E square over A0C. Okay. So this should be roughly the momentum of a photon that is causing a transition between energy levels in a hydrogen atom. Okay. Now, what is the momentum of an electron correspondingly? So the momentum of electron in the hydrogen atom can be sort of roughly understood using uncertainty principle. Suppose if we are looking at an electron in the lowest state, it is bound within some radius, which is roughly taken to be the Bohr radius, A0. So since delta x, delta p is h bar, the momentum of such an electron should be of the order h bar over A0. Okay, remember that we are not making an exact argument here. We are trying to simply understand the magnitudes of the momentum of the electron and the momentum of the photon. So let me call this PE. Okay, and this is P gamma. All right. So the ratio of the momentum of the photon and the electron is basically P gamma over PE. This is h bar k divided by PE, and this is roughly equal to excuse me, E square over A0C divided by h bar over A0 So this is roughly equal to E squared. The A0 part cancels. E square over H bar C. Okay. So if you plug everything in, this will be approximately equal to 1 over 137. Okay. The fine structure constant. So we understand that the momentum of a photon that is causing a transition between energy levels um, is quite low compared to the momentum of the electron. Okay. Um, But of course, in this case, the photon is not just causing a transition between energy levels. It is basically ripping the electron completely out of the hydrogen atom. But even in this case, we can safely make the assumption that the momentum of the photon is not very large typically compared to the momentum of the electron. So all this basically is to say that the magnitude of K in the Hamiltonian here, e to the I k dot r, the K is not a very large quantity, which means we can approximate e to the I k dot r as a series in k dot r. So I can basically say e to the I k dot r is approximately 1 plus I k dot r plus higher order terms. Okay. And we will first work under the assumption that e to the I k dot r is simply equal to 1. Okay. We will neglect all possible terms, even a linear term in k. Okay. Since k is a very small quantity, we will simply put in e to the I k dot r to be equal to 1. Okay. So what does this bias? Okay, and what does the Hamiltonian look like under this assumption? Then the Hamiltonian, I'll simply write the spatial part. The spatial part, let me write the entire thing. It's not very difficult. H tilde is now given by, so remember the e to the I k dot r piece has gone away. So you will have E over 2 mc A0 dot P, right? And times e to the minus I omega t. Okay. So this is what we get when approximating e to the I k dot r to be equal to 1. All right. So again, let us try to understand what this Hamiltonian is in a little more detail in terms of things that we understand, like electric field and so on and so forth. So remember that under this assumption, our A, which was A0 cosine k dot r minus omega t, which we wrote as A0 is 1/2 e to the I k dot r minus omega t plus e to the minus I k dot r minus omega t, right? And then in this two terms, we also discussed the relevant term that causes photoelectric effect is the e to the minus I omega t part. So the part of A that we are interested in is e to the I k dot r minus omega t, right? And now if you make the further assumption that e to the I k dot r is simply unity, then our vector potential A is simply given by A0 times 1/2 e to the minus I omega t. Okay. Which means that since electric field and magnetic field can be derived from the magnetic vector potential, specifically the electric field is given by minus 1 over c dA dt. Remember that we are operating in the Coulomb gauge where phi is 0, so there is no del phi term here. So E would simply be given by I omega over 2c A0 e to the minus I omega t. Okay, so this might come in handy, so please bear this in mind. Okay, all right. So remember that to plug it into the Fermi's golden rule and evaluate the rate of transitions, we would need the matrix elements of the perturbing Hamiltonian between the stationary states, right? Between the initial and the final states. So typically we are going to, so let us write down the rate formula again. Rate of the initial state going to the final state is given by 2 pi over h bar times the absolute value of the perturbing Hamiltonian matrix element between the unperturbed states times a delta function. Okay, so this is what we are looking to understand. So now let us look to understand what is the initial state and what is the final state in this particular problem that we have at hand. Okay, so we have understood what the perturbing Hamiltonian is. So we have to understand what the initial state and final state are. So our initial state by assumption is the ground state of the hydrogen atom. So I0 is 1, 0, 0. Okay, we'll work in the coordinate representation. So in r theta phi, or rather r I0 is basically psi I of r, and this is basically given by square root of 1 over pi A0 cubed e to the minus r over A0. This is the ground state of the hydrogen atom. Okay, so the last lecture, I think I made a mistake in this normalization. If I go back here, I remember. So here I wrote the normalization as 2 pi h bar, which is incorrect. So this is the initial state, which is basically pi A0. Okay, so please make this correction in your notes. All right, so this is my final initial state. What is my final state? Well, my final state is basically the electron, which has basically freed up from the hydrogen atom. So it is going as a free particle. So my F0 is basically a free particle, right? So in the coordinate representation, this is basically given by 2 pi h bar to the 3/2 e to the minus I p dot r. So I'll call this pf because it is a final state momentum, pf dot r divided by h. So these are the initial and the final states that we are looking at for this particular problem. Okay, so now we are looking at the matrix element f h tilde I. Before we actually evaluate the matrix element, let us simply look at it from the point of view of this operator A dot P, and it will also teach us specifically what is the Hamiltonian that we're actually working with. This Hamiltonian that we have derived over here, which I'll put in a box, is actually something that you have seen in a different form. Okay, so we will actually show the equivalence between this form and the form that you have already. I don't seem to be able to draw a box properly. Okay, so let us try to understand this Hamiltonian. So what is the, so if I don't have any electromagnetic radiation, my free particle Hamiltonian is basically p square over 2m plus v of r. Okay, where v of r is of course the Coulomb potential. Okay, so if I calculate r h0, the commutator of r and h0, this is basically equal to the commutator of r with p square over 2m plus the commutator of r with v of r, right? And since the different components of position commute, this will be equal to 0. And this you can evaluate very easily to be IH bar over m times. Okay. So the task of evaluating the matrix element F0 H tilde I0 is basically equal to F0 H tilde E over 2mc times A0 dot P. Okay. Of course, there is an e to the minus I omega t piece as well, but as far as the matrix element is concerned, the e to the minus I omega t will just come out. It's just a constant. So it is just this, right? Which I can rewrite as, remember that A0 is just a classical, some constant vector. So this is A0 dot F0, or rather, you can also pull out all the constants. E over 2mc A0 dot F0 P I0. And I can use this relation up here to rewrite this P as E over 2mc m over IH bar A0 dot F0 R H0 I0. Okay. Remember that H0 is the unperturbed Hamiltonian, and F0 and I0 are the stationary states, which are the eigenstates of the unperturbed Hamiltonian. So what is this equal to? This is E over 2mc A0 dot, let's expand this commutator out. This is R H0 I0 minus H0 R I0. And H0 is a Hermitian operator. In the first one, it acts on I0 to give me the energy of the initial state. The second case, it acts on the H0 on the left and gives me the energy of the final state. So this is E over 2mc m over IH bar. So in the first case, it gives me EI0. The second case, it gives me EF. And what is remaining is A0 dot F0 R I0. I hope that was clear. Okay. Now, EI minus EF is basically H bar omega, which is the energy of the photon that is causing this transition between the initial and the final states. So I can write this as E over 2mc m over IH bar times H bar omega A0 dot F0 R I0. Okay. So if you clean up all these things, you would actually get, what do you get? This M cancels, right? The H bar cancels. So you have E, or rather 1 over 2c omega A0 dot, I will write this as F0 ER I0. Okay. Now, if I put in the time dependence also, which is e to the minus I omega t, which I have not done so, if I simply tag on the time dependence, then F0 H tilde I0 would be given by I, sorry, there is also a 1 over I here. So I'll put in minus I, okay, which is 1 over I. So I'll have I omega over 2c A0 e to the minus I omega t dot F0 minus ER I0. Okay. Now this entire thing is nothing but the electric field. Okay. And the operator E times R is basically the dipole moment operator mu. Okay. So what we have basically understood is that in the approximation that E to the I k dot R is just 1, this entire matrix element can be understood as the matrix element of mu dot E between the initial and the final states. Okay. So even though we are using what is looking like a rather complicated form for the perturbing Hamiltonian, which is A0 dot P times e to the minus I omega t and so on and so forth, what we essentially have is basically a mu dot E kind of interaction, okay, which is exactly equivalent to what we have. So this is the reason why that this approximation e to the I k dot R equal to 1 is called the electric dipole approximation, because in this approximation, the perturbing Hamiltonian is basically the dipole moment operator, mu dot E. Okay, so this is important to understand. Okay, so we will not be using the mu dot E explicitly. We will go back to A0 dot P because things are a little easier to evaluate if I have this explicit term. But you should understand that even though it looks rather complicated, in this approximation, of course, things are rather simple. Of course, if I put in higher order corrections, I will get quadrupole corrections, octupole corrections, and so on and so forth. All right, so let us go back to evaluating the matrix element, because that is fundamentally what we want to do. So we want to understand F0 H tilde I0, right? So this is equal to, so I'll follow Shankar's approach and basically club all the constants to some n. And basically what I have is e to the minus I. I'm working in the coordinate space representation. So pf dot r divided by h bar a0 dot minus ih bar del acting on e to the minus r over a0 d cubed r. Okay, so this is in the r representation. So I advise you to work this out explicitly in case you're having difficulty understanding this is what this is. Simply f0 h tilde I0 is basically what we're basically doing is plugging in d cubed r prime, the completeness relation 2 times f0 r h tilde r prime I0. Okay, this is what we are doing. Now this of course is the final state wave function in the R representation. This is the initial state wave function in the R representation. And this is the matrix element of the Hamiltonian in the coordinate representation. But of course, the matrix element of the Hamiltonian in the coordinate representation is basically, remember the Hamiltonian is basically the momentum operator. So in the coordinate representation, this has the form minus ih del bar. And there is a delta function between R and R prime. So if you use the delta function between R and R prime, you can collapse this into the form that I have given over here. Okay, so I encourage you to do this exercise yourself. So evaluating the matrix element, we get where n, of course, is there is an E over 2 MC from the H tilde part. There is a 1 over 2 pi H bar to the 3/2 from the final state wave function. And there is a 1 over pi A0 cubed to the 1/2 from the initial state wave function, the ground state of the hydrogen atom. So I'm clubbing all these things into one constant that I'm calling n. Okay. So the remaining is quite straightforward to do. I simply have to evaluate this matrix element. So the first thing that I would do is do an integration by parts and push the del to the left with a cost of a negative sign. So f0 h tilde I0 can be given by, of course, if I use a partial integration and push the del to the left, the del will now act on the IPF dot R over H bar, right? So I will get n minus I H bar, and when the del acts on IPF dot R over H bar, it's going to spit out a factor of minus I PF over H bar. So there is an A0 which I will pull out, dot minus I PF over H bar, which is the action of del on the left hand side. Okay. Of course, there is also another negative sign because I have done a partial integration and thrown away the surface term, times integral d cubed r e to the minus I PF dot r divided by H bar e to the minus r over Az. Okay. So the remaining is actually a straightforward integral. I'll just set this up and quote the final result. So f0 h tilde I0 is therefore given by n times A0 dot pf. The h bar cancels and all the i's and the negative signs collapse to +1. Integral d cubed r e to the minus I pf dot r over h bar e to the minus r over Az. Okay. So we will evaluate this matrix element and stop, because the rest we will continue in a separate module or in the tutorial. So how do you evaluate this matrix, this integration? This is actually not very difficult. The way you would do this is basically the choice of my z-axis is free. Right? How I position my coordinate axis is completely up to me, and Pf is the momentum of the final state electron, which is basically a free electron. So I will position my axis such that Pf coincides with the z-axis. So if Pf coincides with the z-axis, then Pf dot r is basically P times r times cosine theta. So I can use this. So align PF along the z-axis. Okay, so my integral is d cubed r e to the minus I PF r cosine theta divided by h bar. Here PF and r are basically the magnitudes of PF and r, e to the minus r over a0. Of course, we have to be a little careful doing the angular integrations because there is an explicit dependence on theta here. I can still do the phi integration trivially. There is no phi dependence. So integration phi is simply going to give me a factor of 2 pi. Okay. The integration over the theta part would be, I'll write this is d of cosine theta from minus 1 to 1, okay, which is basically d theta sine theta. I'm writing it as d of cosine theta, and I'm using the extra negative sign to flip the limits from minus 1 to 1. E to the minus I PF r cosine theta over h bar times e to the minus r over a0 r square dr, where r integration goes from 0 to infinity as usual. Okay. So the first integration is very easy. So this is basically 2 pi times e to the minus I PF r over h bar minus e to the I PF r over h bar divided by minus I PF r over h bar. This is the theta integration times e to the minus r over a0 r square dr. Okay. So put everything together and your f h tilde I finally becomes n a0 dot pf. Okay. That comes from the overall factor right here times a 2 pi times h bar minus h bar over I pf, all of these guys outside, times integral 0 to infinity. This is basically minus 2I sine PFR over h bar e to the minus r over a0. There is one factor of r square here and a factor of r in the denominator here. So that takes care of one factor of r in the numerator. Okay. This integration, though difficult, can be done using usual techniques. And I will simply quote the result. So the R, rate of transition from the initial to the final states in this particular case, is now given by 2 pi over h bar times, remember that the rate is the absolute value of this guy. Okay. The absolute value of this guy is e over 2mc the whole square 1 over 8 pi cubed h bar cubed 1 over pi a0 cubed. That comes from the um, two factors of normalization times a0 dot pf mod square times 64 pi square a0 to the 6th divided by 1 plus and then there's a delta function ef minus ei minus h bar. Okay, so basically what we've said is that this integration d cubed r e to the minus I pf r cosine theta over h bar e to the minus r over a0 r square dr, so d cubed r excuse me, is 8 pi divided by a0 divided by 1 over a0 square plus PF over H bar the whole square, this quantity. Okay, so once you get this answer for the integration, the rate is straightforward because you simply have to square this quantity to get the rate of transition. So what we have basically shown here is a demonstration of how the Fermi's golden rule can be applied in the case of uh, photoelectric effect or ionization of a hydrogen atom. So you're basically impinging photons externally and knocking off the electron in the hydrogen atom, basically completely out of the hydrogen atom so that the electron becomes a free particle. Okay, so we'll continue discussing the physics of this in the next module.